Hello everyone. In this video, we will be discussing atmospheric lifting and cyclones. The interactions between Earth's surface and its overlying air create regional air masses with uniform temperature, humidity, and stability characteristics. Each of these distinctive bodies of air is called an air mass. They initially reflect the characteristics of their source region, but then move away from that source region and gradually take on the characteristics of their new location as they migrate with the winds. We classify air masses generally according to the moisture and temperature characteristics of their source regions. The first letter in the classification indicates moisture of the air mass. So M would stand for maritime or wet or moist air mass, and a C stands for continental or relatively dry air mass. Temperature is indicated in the second letter of the air mass label. So we have A for Arctic, P for polar, T for tropical, E for equatorial, and AA for Antarctic. And again, these indicate the temperature of the air mass. The first image on top shows a winter pattern of air masses in North America. The polar and Arctic air masses, the MP, CP, and CA, shift south with the subsolar point in the winter. And then we see the bottom image shows the summer patterns of air masses in North America. The tropical air masses, the MT and CT, shift north during the summer. So the more unstable MT air mass in the southeast brings summer thunderstorms. Continental polar, or CP, air masses are found only in the northern hemisphere. They are most developed in winter and cold weather conditions and typically have cold, stable air, clear skies, and high pressure. The southern hemisphere lacks the necessary continental land masses at high latitudes to create a CP air mass. Maritime polar air masses occur over the northern Atlantic and Pacific Oceans and feature cool, moist, unstable conditions throughout the year. And the maritime tropical, or the MT, air masses include the MT Gulf Atlantic and the MT Pacific. High humidity in the east and Midwest is from the MT Gulf Atlantic air mass, which is particularly unstable and active from late spring to early fall. The MT Pacific air mass is stable to conditionally unstable and is lower in moisture content and available energy. Partly because of these characteristics of the MT Pacific air mass, the southwestern United States receives lower average precipitation than the rest of the country. As air masses migrate from source regions, they take on temperatures and humidity characteristics of the land over which they pass. So, for example, an MT Gulf Atlantic air mass may carry humidity to Chicago, but it will gradually lose its initial characteristics of high humidity and warmth with each day's passage northward. Similarly, below freezing temperatures occasionally reach into southern Texas and Florida, brought by an invading winter CP air mass from the north. Modification of CP air as it moves south and east produces higher snowfall to the east of each of the Great Lakes. As below freezing air passes over the warmer Great Lakes, it absorbs heat energy and moisture from the lake surfaces, and this produces heavy lake effect snowfall. Air must be cooled to its dew point temperature to condense, form clouds, and bring rain. When air is lifted, it expands and cools adiabatically. The four main lifting mechanisms are convergent lifting, convectional lifting, orographic lifting, and frontal lifting. In this slide, we see an example of convergent lifting. Convergent lifting is when air flows towards an area of low pressure. So, for example, the southeast and northeast trade winds converge along the equatorial region, forming the Intertropical Convergence Zone, or the ITCZ. This is a region of frequent cumulonimbus clouds and high average annual precipitation. This slide shows convectional lifting, which is local surface heating that causes warm air to rise. Convectional lifting can be small scale, as in a field in the image we see here, but it can also affect a larger region. Orographic lifting is when air is lifted upward by a barrier, such as a mountain range. If the atmosphere is stable, lenticular clouds may form. Unstable conditions can form a line of cumulus and cumulonimbus clouds. Because orographic lifting happens regardless of atmospheric stability, it is the most consistent lifting mechanism. It also enhances rain produced by convectional lifting and frontal lifting. The wetter, intercepting slope is called the windward slope, and the drier, far side slope is the leeward slope. Moisture condenses from the lifting air mass on the windward side of the mountain. On the leeward side, the sinking air heats by compression, and any remaining water in the air evaporates. Warm fronts are indicated on weather maps as a line with semicircles facing in the direction of the frontal movement. Because warm air is less dense, an advancing warm air mass slides up over the cooler air and tends to push the cooler air into the characteristic wedge shape of a warm front. A cold front is shown by a line with triangle spikes that point in the direction of the frontal movement along an advancing CP or MP air mass. The steep face of the cold front is caused by its cold, dense air rapidly lifting the less dense air of the warmer air mass. Cold fronts travel faster than warm fronts because the cold, dense air easily lifts the warmer, less dense air. As the cold front advances, the wind direction shifts and the temperature and air pressure both drop. As the line of most intense lifting passes, usually just ahead of the front itself, air pressure drops to a local low. Clouds may build along the cold front into cumulonimbus clouds, which may appear as an advancing wall of clouds. Precipitation usually is heavy and can be accompanied by hail, lightning, and thunder. Warm and cold fronts often are found together, spiraling around a center of low pressure and forming a storm called a mid-latitude cyclone. These storms are formed by the conflict between warm, moist tropical air masses and cool, dry polar air masses. The air masses combine to form a warm front and a cold front spiraling around the converging rising air of a low pressure center. They are called wave cyclones because, when seen from above, the two fronts resemble a wave. Wave cyclones, which can be 1,000 miles wide, or 1,600 kilometers, dominate weather patterns in the middle and higher latitudes of both the northern and the southern hemispheres. A mid-latitude cyclone can form along the polar front, particularly in the region of the Icelandic and Aleutian low-pressure cells in the northern hemisphere. Other areas associated with cyclone development and intensification include the eastern slope of the Rocky Mountains, the Gulf Coast, and the eastern seaboard. The high-speed winds of the jet streams guide cyclonic systems and their air masses along storm tracks. Typical storm tracks in North America follow the subsolar point and shift north with the subsolar point toward the poles in summer and south toward the equator in winter. As the storm tracks begin to shift northward in the spring, CP and MT air masses are in their clearest conflict. This is the time of strongest frontal activity, featuring thunderstorms and tornadoes. The flow of energy across Earth can set into motion destructive, violent weather. On a humid summer afternoon, the combination of warm, humid air and the sun's energy can quickly lead to the formation of dark, threatening clouds, dangerous lightning strikes, and stormy conditions. Thunderstorms form during unstable atmospheric conditions. The life cycle of a thunderstorm has 3 stages of development. In the first stage, warm, moist air is lifted, often by convergent or convective lifting. As the air rises, it cools by expansion. When the lifted air cools to the dew point temperature, condensation occurs, releasing latent heat. If atmospheric conditions are unstable, the air will continue to rise. The rising air creates an area of low pressure at the base of the cloud, which draws in more warm, moist air, causing updrafts. The second stage occurs when the warm air rises until it reaches the top of the troposphere, called the tropopause, or the top is sheared off by strong winds. Here, the air spreads out horizontally, creating a distinctive anvil shape. The water droplets in the cloud coalesce into larger drops and freeze into ice once they reach freezing altitude. If the updrafts are strong enough, these ice particles will grow until they fall as hail. During this phase of the thunderstorm, the rising air causes strong updrafts, and the falling rain causes strong downdrafts. The final phase of the thunderstorm occurs when there is no longer sufficient warm, moist air to support the updrafts, and the storm is dominated by the downdrafts. Lightning strikes Earth over 8 million times each day. Lightning refers to flashes of light caused by enormous electrical discharges, hundreds of millions of volts, that briefly heat the air to temperatures of 15,000 to 30,000 degrees Celsius, or 27,000 to 54,000 degrees Fahrenheit. A buildup of electrical energy within a cumulonimbus cloud or between the cloud and the ground creates lightning. The violent expansion of this abruptly heated air sends shock waves through the atmosphere as the sonic boom of thunder. Lightning causes nearly 200 deaths and thousands of injuries each year in the United States and Canada. 90% of all strikes occur over land in response to increased convection over relatively warmer land surfaces. When updrafts within large cumulonimbus clouds combine with horizontally rotating bodies of air, tornadoes can form. Because of the effect of friction close to the ground, wind speeds are higher than wind speeds close to the ground. The difference between wind speeds next to the ground and wind speeds aloft produce a horizontally rotating body of air that moves along like a rolling pin. When this horizontally rotating body of air runs into an updraft within a cumulonimbus cloud, the horizontally rotating body of air is tipped up and rotates vertically. The spinning, rising column of air forms a mesocyclone. A mature mesocyclone will produce heavy rain, large hail, blustery winds, and lightning. Some mature mesocyclones will generate tornado activity. As more moist air is drawn up into the mesocyclone, more energy is liberated, and the rotation of the air increases speed. The narrower the mesocyclone, the faster the spin of air being sucked into the rotation. The rotation of the mesocyclone is visible as are smaller, dark gray funnel clouds that pulse from the bottom side of the parent cloud. Pressure inside a tornado is usually about 10% less than that of the surrounding air. This steep pressure gradient causes high wind speeds. North America experiences more tornadoes than anywhere on Earth because its latitudinal position and topography permit contrasting air masses to collide. Tornadoes have struck all 50 states. A powerful demonstration of the transfer of energy from the tropics to the poles is the tropical cyclone. Approximately 80 tropical cyclones occur annually worldwide, and 45 of those are powerful enough to be classified as hurricanes. A full-fledged hurricane has wind speeds greater than 119 kilometers per hour, or 74 miles per hour. They have regional names. Hurricanes occur in North America, typhoons in the Western Pacific, and cyclones in Indonesia, Bangladesh, and India. Tropical cyclones form without fronts or conflicting air masses. Sea surface temperatures over 26 degrees Celsius or 79 degrees Fahrenheit provide the water vapor and latent heat energy to fuel these storms. Tropical cyclones convert heat energy from the ocean into mechanical energy in the wind. The warmer the ocean and atmosphere, the more intense and powerful the storm. Tropical cyclone season for the Atlantic is from June 1st to November 30th each year. Cyclones begin with easterly waves, slow-moving waves of low pressure that move from east to west in the trade wind belt of the tropics. Tropical cyclones form along the eastern side of these easterly waves, a place of convergence and rainfall. Surface air flows into the low-pressure area, begins rotating, ascends, and diverges aloft. This important divergence acts as a chimney, pulling more moist air into the developing system. A weak tropical disturbance is the first step toward the development of a full-fledged hurricane. Hurricanes are unable to form within 500 kilometers or 300 miles of the equator because the Coriolis force is not strong enough there for the storm to rotate. Tropical cyclones range in diameter from 160 kilometers or 100 miles to some western Pacific super typhoons that reach 1,300 to 1,600 kilometers or 800 to 1,000 miles. Vertically, these storms occupy the full height of the troposphere. The spiraling clouds form dense rain bands, with the central area designated as the eye. Around the eye swirls a thunderstorm cloud called the eye wall. This is an area of the most intense precipitation. In the midst of the winds and torrential rains, the eye is quiet and warm, with even a glimpse of blue sky or stars. Hurricane Sandy began in the Caribbean Sea on October 22, 2012. While over the Bahamas, it underwent complex changes, growing in diameter while weakening in intensity. Sandy moved northeastward parallel to the eastern coast of the United States and gained intensity while passing over the warmer waters of the Gulf Stream. Sandy became a post-tropical cyclone, unofficially called Superstorm Sandy, when it was no longer fueled by the release of latent heat of condensation close to the center of low pressure, but by conflicting air masses more similar to the mid-latitude cyclones. By the time Sandy dissipated, it had become the largest Atlantic basin storm by diameter, claimed 286 lives in 7 countries, affected 24 states in the United States, and caused almost $70 billion in damage. Hurricanes are powered by the latent heat of condensation of water vapor that has evaporated from warm tropical waters. Record sea surface temperatures across the globe produce warmer water, and the natural mixing by storms bring up more heat. Research has correlated longer tropical storm lifetimes and greater intensity with rising storm intensity. As oceans warm, the energy available to fuel tropical cyclones is increasing. Continued ocean warming, sea level rise, and the current trend of increased coastal populations will likely result in substantial hurricane-related property losses. Okay, that's it for this video. I will see you in the next one.